All right, hello there. We're going to do section 5.3 today. We're almost done with linear algebra. We only have 3 more sections in chapter 6 to do. And so here we go with our topic, diagonalization. So you've learned that eigenvalues of a diagonal matrix are really easy to find because they're the entries on the diagonal. So it's often useful to diagonalize a matrix so that you can find the eigenvalues. And it's also very easy to find powers of diagonal matrices. All right, so we're going to do that right here. In example 1, we have D is 5, 0, 0, 4. Let's find D2. So if I want to find D2, I would have to basically multiply 5, 0, 0, 4 times itself. All right, so if you do that, you notice that you have 5, 0 times 5, 0, so you get 25, 0. And 25 plus 0 is 25, and then you get 5, 0, and 0, 4, so you get 0. So there's my first two numbers, so 25 is 5 squared, and then 0. If I do that for the second column, or the second row, I have 0, 4 times 5, 0, so it's 0. 0, 4, 0, 4, so I get 0 plus 16, which is 16. So I get 0 and then 4 squared. So if we did D3, it would turn out very similar to that. We would get 5 to the third, 0, 0, and then 4 to the third. So basically the formula is this. When you do this, when we do take that D matrix and do it to a power, we'd end up getting 5 to the k, 0, 0, and 4 to the k. Oops. All right, so if you want to find a power of a non-diagonal matrix, an efficient way of doing this is to do what's called diagonalize the matrix, like to diagonalize it first, and then you can easily do the power of it. All right, so let's look at our steps for diagonalizing. So one main thing here, we have to look at something called similar matrices, and so that was at the end of the very last, or it was in the last section, but you didn't really kind of notice it because it was just like a little definition to the side. And also this last part here was, this next part was in there too, but right at the end, so it was just kind of easy to just bypass over. So you learned in the last section that what it meant to be similar. Basically, similar matrices, you can turn one into the other by simple multiplication, and then to go back to the one you started with, you reverse that multiplication. So you have these two little pieces right here. So that's what we're interested in finding. We're interested in like factoring up a matrix into these things, into this like p and p negative 1. And what's going to happen right there is that what we're going to put right in the center right here is we're going to put our diagonal matrix. So that'll be easy to take power of. All right, so here's the steps we're going to do. We're going to find the characteristic equation, just like we did in the last couple sections. We're going to find the eigenvectors, and then we're going to make a matrix with the eigenvectors as its columns. And the matrix D is going to have the eigenvalues along the diagonal. And then we're going to check it out and make sure we factored it correctly, that it multiplies back to the original. All right, so here we go with the nice easy one here. So in example 2 here, so remember that main equation that you had earlier, like a minus lambda I, to get the determinant of that is equal to 0. That's your characteristic equation. So I'd have 1 minus lambda, 1, negative 2, and 4 minus lambda, the determinant of that, equal to 0. All right, and so, sorry, I didn't like how that looked. All right, so my determinant, I would get 1 minus lambda times 4 minus lambda plus 2 equals 0. So you clean that up, it turns into lambda squared minus 5 lambda plus 6 equals 0. So that factors into lambda minus 3 and lambda minus 2. So I get my two eigenvalues as lambda equals 2 and 3. So I got to find their corresponding eigenvectors. So when you have lambda equals 2, so basically what we're doing is putting that back over here. And so if I put a 2 there, I get negative 1, 1, negative 2, and 2. I augment that with zeros, and you do your RF. You come out to 1, negative 1, 0, and 0, 0, 0. So x2 is free right there. x1 is equal to x2. And so I get my corresponding eigenvector for this to be 1, 1. Well, then I got to do lambda equals 3 as well. So by the same process as we just did right there, I would put 3 over here, and then do the same thing I just did, let me just tell you that my eigenvector for this is going to be 0.5 and 1. All right, so it's time to make our matrices. So my D matrix is going to be a diagonal matrix, so zeros everywhere else except the diagonal. The diagonal is going to have 2 and 3, my eigenvalues. Now, it doesn't matter which order you put those in, but it does matter when you make matrix P, you put the vectors in the same order that the D was in. So I put 2 first in the diagonal matrix, and so I'm going to put the eigenvector that went with that first over here. So I'm going to put 1, 1, and then I'm going to put 0.5 and 1. So I also have to find the inverse of P. So remember, I do 1 over the determinant. So I'm going to find that to the side. You don't have to write that down here. So my inverse, so P negative 1, is 1 over the determinant of P is 1 minus 1/2. So that would be 1/2 right here. Then I switch around the ones, but you don't notice that. Then I make these negative. So if I multiply that out, this turns into a 2. So basically you get 2, negative 1, negative 2, and 2 for my P negative 1. So let me fill that in. 2, negative 2, negative 1, and 2. All right, so now it's time to check this out and see if it all works. So what we're trying to check to see is we're checking that A is really P times D times P negative 1. All right, so let's see. P is 1 and 0.5 and 1, 1. D is my 2, 0, 0, 3. And then P negative 1 is 2, negative 1, negative 2, 2. All right, so you could do this any way you want. I'm just going to go ahead and do this one first. So when I multiply that, I have 1 times 2, so that's 2 plus nothing down below. So 2. Then I have 1.5 times 0, 3, so I get 0 for that. In the second row, I have 1, 1 times 2, 0, so I get 2. And I have 1, 1 times 0, 3, so I get 3. All right, so then let's multiply it with 2, negative 1, negative 2, 2. All right, and so I end up getting, let's see, 4 minus nothing. All right, so something's going wrong here. Let me make sure I didn't make a mistake here. So that's 2 and nothing, and then, I did make a mistake. 0, when I did this multiplication right up here, this is wrong. All right, so let's see. So I did something wrong there, so this is wrong. So let's see. Let me erase that right here. Oh, crap. All right, well, I'll just do it all over again. Sorry. Oh my God, my eraser. All right, 1, 1. Here we go, too fast. All right, so 1 and 0.5 times 2 and 0, that's 2. 1 and 0.5 times 0 and 3, that is 1.5. All right, there we go. Now, then I get 2, and then I get 3. All right, so now this is multiplied by 2, negative 1, negative 2, 2. All right, so I get 4 minus 3, so that's 1, good. Then when I do this and this, I get negative 2 plus 3, so I get 1. All right, and then on the bottom row, 2, 3 times 2, negative 2, I get 4 minus 6, so good, negative 2. And then finally, 2, 3 times negative 1, 2, I get negative 2 and 6, so I get 4. Phew, sorry about that. All right, it's late at night here. All right, for me at least. I don't know when you're watching this, but anyway, so it did it all. So basically what you've done is you've kind of, like we did a long time ago with like our LU factorization in a way. I mean, it's different, but what you've done is you have turned A into these 3 pieces. All right. So I'm going to kind of shortcut here, but we would end up doing similar things in this problem. So let's go ahead and do our, we will find our characteristic equation, and then I'm just going to kind of like bypass some of the other pieces that you would do in your calculator. All right, so my characteristic equation, like we did right here, I would have 2 minus lambda, 0 and 0 would stay, 1/2, 3 minus lambda, 1, 0, 0, and 2 minus lambda. So do the determinant equal to 0. So pretty sure that the best thing to do is to use this row. I'm just going to use this row. Oh, let me take that back. When I just use the top one. So here and here, right? So I'm going to use that top corner. So 2 minus lambda. It's going to stick around. And then I have to basically then do the determinant of the other 4 left multiplied by the 2 minus lambda. Well, the determinant of the other 4 is going to be 3 minus lambda and 2 minus lambda. How convenient. So my eigenvalues are 2, 2, and 3. All right. So I'm going to go ahead and find the eigenvectors for that. So we know our diagonal matrix right now. Our D matrix is 2, 0, 0, 0, 2, 0, and 0, 0, 3. All right, now I'm going to be in trouble here if 2 does not produce 2 eigenvectors. Okay, so let's test it out. So when I put 2 in there, you get a matrix of 0, 0, 0 on top. You get 1/2, 1 and 1 in the middle, and then 0, 0, 0 on the bottom. So you actually do get 2 eigenvectors out of this. So when lambda equals 2, your eigenvector, one of your eigenvectors, turns out to -2, 1, and 0. The other one turns out to -2, 0, and 1. And I'm putting them in the first 2 columns because that is the same as I have in my D matrix. And the eigenvector for 3 turns out to be 0, 1, 0. There we go. And then you can plug that into your calculator. You find p -1 in your calculator, and you end up getting -1/2, 0, -1, 0, 0, 1, 1/2, 1, 1. And there you go. All right. So of course that'd be a lot harder by hand. All right. So in example 4. So we're going to find a formula for AK. And so we know all the matrices, we don't have to find them. So basically what we have right now is we have our equation here. So I have right now that 6, 2, -1, 3 is equal to 1, 1, 1, 2 times D, which is 5, 0, 0, 4. Times p -1 is 2, -1, -1, 1. So it turns out that if you want, just like we did in the first example over there, if you want to put a power on this, all you have to do is put a power on here. And so you can test that out in your calculator because I don't want to take the time to show you that right here. But anyway, like if you want to do a matrix to a power, if you have diagonalized it, then it's just like basically like you do a power on a couple numbers in the middle, and then you basically do 2 matrix multiplications and you have it. Okay. All right. So it turns out to be really easy. All right. So we're going to do that down here. And you can test it out in your calculator if you want. Like you could type this really easily into your calculator, 2x2 matrix, take it to the 10th power and test it out. So we have to diagonalize this. So we have to find the characteristic equation. So I have 1 minus lambda, -2, 3, -4 minus lambda. Determinant equals 0. So you get 1 minus lambda times -4 minus lambda. And let's see, plus 6 equals 0. So it turns out my characteristic equation, I have lambda squared plus 3 lambda plus 2. And so you get lambda equals -1 and -2. All right, so I will tell you then your diagonal matrix is -1, 0, 0, -2. And remember, it doesn't really matter. You just have to make sure you put your things in the same order. So the eigenvector for -1 turns out to be 1, 1. Let me see if I have it in the right order. Let me see. Yep, it's 1, 1. I'm going to put that up. I'm sorry, for -1. Yeah. I had it in a different order on my paper. So the eigenvector for -1 is 1, 1. Now, the eigenvector for -2 actually turns out to be something kind of ugly. It turns into 2/3 and 1. But remember, you can use that or any multiple of that. So I'm going to go ahead and multiply that by 3, and it becomes 2 and 3. Okay. All right. And then I just have to make sure that I use that to find p-1. So if you do your, determinant, 1 over the determinant, and then flip everything around like you're supposed to and do negatives, your p-1 turns into -1, 1, 3, and -2. All right. So if you want to do a to the 10th, so a to the 10th would just be p, 1, 2, 1, 3, times your d, -1, -2, 0, 0 here. And we're going to take these to the 10th power. So this is going to be to the 10th power, and that's going to be to the 10th power. And then times p-1, well, that's -1, 3, 1, and -2. So if you do those quick multiplications, you will see that a to the 10th comes out to -2,045, -3,069, 2,046, and 3,070. All right. But it's easier than multiplying a by itself 10 times. I know it seems like a lot of work, but to do this, but it's easier than doing the other thing 10 times because it just will get kind of tedious there. All right. All right, so a square matrix is said to be diagonalizable if A is similar to a diagonal matrix. When is A diagonalizable? So you have to make sure, like I think I stated earlier, I think when we had this problem back here, remember we had the repeat eigenvalues. So remember that from last section, if you have a multiplicity of 2, that means you could have 1 eigenvector or 2 eigenvectors for this eigenvalue. And so it is either or. And so if something's going to be diagonalizable, it has to actually be the max, because you have to have enough vectors to fit into your P matrix. Okay, all right, and so that's just the next little bit right there. So that's just this little piece just telling you that rule right there. And so example 6 is saying to why is A diagonalizable? Well, when something has 3 separate three separate eigenvalues, then there's going to be 3 separate eigenvectors. And so I know I'm going to be able to do this. So your eigenvalues are 2, 6, and 1, all totally different. So they each have to have an eigenvector corresponding to them. And it turns out if you actually work it out, they do. So 2 has an eigenvector of 2, -1, 4. 1 has an eigenvector of 0, 0, 1. And 6 has an eigenvector of 0, 5, 2. So you have a linearly independent set of eigenvectors. All right. So that's what theorem 6 says. An n by n matrix with n distinct eigenvalues is diagonalizable. All right. So great. We already discovered that. So in example 7, show that this is not diagonalizable. So what's happening here is I have the same 2 eigenvalues. So my eigenvalues, a diagonal matrix, I have 2s across the diagonal and 0 on the top. Actually, it's not a diagonal matrix. It's like a upper matrix or a lower matrix, I guess it's called. Sorry, I get these confused. And so 2 is my eigenvalues. So, but when I do this, when I use 2 as my eigenvalue, so if I go ahead and, do A equals, I'm sorry, not A equals. If I do A minus 2 times I will get 0, 0, 1, and 0. And so when I try to augment this with zeros, what happens is I see x2 is free and x1 is 0. So the only eigenvector I get from this for this eigenvalue is 0, 1. I only get one eigenvector, and I'm supposed to have 2. So that is why it is not diagonalizable. Okay, so this last little theorem here, it says for k between 1 and p, the dimension of the eigenspace is less than or equal to the multiplicity of the eigenvalue. Okay, so the multiplicity matters, right? We learned that before, that like if you have a multiplicity of 3, you could have, 1 or 2 or 3 eigenvectors for that eigenvalue, right? Part B, the matrix is diagonalizable if and only if the sum of the dimensions of the distinct eigenspaces equals n. So you have to have enough eigenvectors to match your size of your matrix. Okay. All right. And part C, if A is diagonalizable and BK is a basis for the eigenspace corresponding to the lambdas, all right, for each K, then the total collection of the vectors in the sets is an eigenvector basis for Rn. So that's kind of like what this produced for us here. All right, and that is it. There are your few problems for homework, and we are done with chapter